Hi everybody, welcome to day 4. We've passed the halfway point in the six-week lecture series on how to program in Python. Today we're going to build on what we accomplished last week. As you recall, we developed a file object to represent the FASTA sequence database last week, and we're able to read it in and count how many protein entries there were. So that's a great start, but today we're going to get a lot closer to our goal. And along the way, we're going to try to make the software we're creating more robust. So I'm going to talk a lot about exceptions, which are ways to protect your software against the unexpected. So we'll talk about that subject first. And then we're going to talk about a way to streamline how to count different letters through something called counters that are part of this collections library. So today we'll start with a brief overview of those two things and then move into the code itself. So I would start by saying that exceptions are useful in code, and they're not unique to Python. They happen in other languages as well. I first encountered them in Java, for example. But exceptions are useful when some of your expectations about what certain variables should be set to and so on are not met. So imagine that you're trying to process some input as a number, but that your variable, instead of equaling 700, for example, is equal to the letter A. How can you do math with the letter A, for example? So that's a case where you would develop an exception. It may be that you tried to do something against the rules. What if the user who was working with our software instructed us to use as a FASTA file something that was not a FASTA file? Maybe it was a Word document. Well, we can't read that using the same strategies as we use for reading text files, so that's not okay. So something like that would be going against the rules, basically, that you have set up for processing a file of one type, but it's something else. The other possibility is that you may have actual security violations. What if the user dtab owns a file and you, mpo, are trying to make use of that file and you're not allowed to read it because it's owned by somebody else? That would be a security violation. So that's the second possibility. And of course there are all sorts of well-meaning things that happen that can also cause your software to break. So imagine trying to read a file that someone has provided on the command line, but they mistyped the file name. If you do something like that, you will try to read a file that does not exist. Also, not feasible, and another action that can cause an exception. So I'm going to explain that this looks quite a lot like the whole if-else kind of structure. It's indented the same way, but it's handled quite differently. We have a section of code that's indented under try. So try and exception, try and accept are these two pieces that we're working with. So the try code is definitely going to be executed, right? So we're going to start with this first line and keep going all the way through there, unless doing one of those commands triggers an exception. So if there is an exception within this code indented by try, the handling code, the exception handling code, follows the except part after it. So here we can see that our code is relatively straightforward. We want to print the value of 1 divided by 0, and if an exception occurs as part of that, we're going to handle it in this except section. And in this case, the exception that we're looking for is called a zero division error. If an error of that sort happens, then it will print division by 0 is not allowed. That's pretty straightforward, I think. So what is the value of 0 divided by 1? 0 divided by 1 is 0, actually. But if you invert that, if you put 1 over 0, right, it's an infinite value. And our software will throw an exception in a case like that for a zero division error. So here we can simply state, try to execute this code. If you run into this particular type of problem, here's how to act on that. I would point out that the code base that shows up in these slides also appears in one of the files that you should have downloaded yesterday. I have the file right here, tinkering. I called it with today's date, August 1st tinkering. So all of that is in that file. Okay, so let's look at a slightly more complex example. One of the things that we frequently want to do when we write software is ask the users for input. And I've sort of bypassed that because we've been talking about how to manipulate a particular file. But I wanted to give one example of that. So here we have a section of a try section for this function that spans quite a few functions here. See, we've got 5 different lines that we're going to try to execute. It is possible, however, that our attempt to execute this code is going to run into trouble because we don't really know what users are going to do in response to our question. So this top line, let me see, okay, so your number equals integer of input, what number shall I check, is a little complex. Let me try to unfold that. When it incorporates this input function right here, remember it's you can tell it's a function because it has these parentheses after it. When the code executes input whatever, it is going to prompt the user with this code, with the text on screen, what number shall I check? And then the cursor is going to be blinking 1 space after that question mark. And this is all the prompting that the user is going to get. What number shall I check? So somebody enters a number here, and ideally that number is then returned from the input function. So the users enter a number, that number is returned by input, that number is passed to integer, the integer function, which tries to turn whatever value, whatever string has been entered by the user, turning that into a number. That number in turn is then assigned to be your number. So I'm going to try to do a quick example of that because I think that will be, oops, sorry, I always misspell Python, I'm not sure quite sure why. So if I just say response equals input, tell me something. I'm going to add a colon and a quote, a space, and then a quote. You can see that the interpreter immediately responds with, tell me something. I slept really well last night. Did everybody sleep really well last night? Yes. We've got some yeses and we've got some nos. Okay, well, I take migraine medication at night, and that lets me sleep like a baby. I sleep amazingly well. So I slept really well last night. Okay, and that's it. You see, nothing happened, apparently. But remember that we told the software we want to receive whatever was entered in input as response. So now if I type response, I see that that variable has been set to this string. Everyone sees how that works? All right, now that's a little different than what happens if we say something like my number equals the integer version of input. Give me a number from 1 to 10. Oh, do you see what happened there? The software is responding with ... What does that mean? This is an ellipsis. It says it's still expecting something from me. Right, so I want you to count how many left parentheses you have in the line and how many right parentheses. You see, I have an open parenthesis opening the integer function and an open parenthesis at the input function, and I close the input function, but I forgot to close the integer. So I just need to type close parenthesis, and now it can go ahead to execute that. Did you see the error? You have to have as many right parentheses as you have left parentheses, or something's wrong. So it was waiting for me to finish that line. So now I enter the number 7. All right. Now if I type in my number, that's all fine. Now I'm going to repeat that command. This time I'm going to add in the second parenthesis so I don't have to redo that. Now I'm going to play some silly games here. I'm going to enter the number 12 instead. So why is that succeeding? It is succeeding in capturing the number 12, even though the prompt said, give me a number from 1 to 10. Python only knows that it is trying to receive a number here. That's what that int part is all about. Just the fact that I told the user I want a number between 1 and 10 does not mean that they're going to give me a number between 1 and 10. Users are deceitful, and this is a very important lesson to internalize as a new programmer. Users are consistently going to do something other than what you tell them to do. I'm going to repeat this, and this time I'm going to give them a number between 1 and 10 that's structured a little differently. Okay, those are the first 6 digits of pi. You see how that one actually generated an error. In this case, the integer function is trying to convert whatever string you give it, in this case 3.14159, into an integer. And it can't do that. It would have to round that number, that value. So maybe if I said something like, oh, I'm not actually sure this is the right syntax, but let me try it anyway. If I enter that instead, now if I type 3.14, am I okay? I am. So we see that how we try to cast what someone has typed into a number is going to change what kind of values are there. And of course, whether you have float or int there, if someone says purple in response to this question, and yes, users will do stuff like that to your precious software, we get another kind of error. So both of these, giving it a floating number when it was asking for an integer, gives you a value error. And here, giving it a string of letters instead of numbers when it expects an integer will also give it a value error. So being able to trap for a value error, being able to catch by a try and except case is really good. Okay, so I realized that all of that tied up in just this one line, right? But I wanted to give some examples of how that plays out to make it a little clearer. And then I played another silly, goodness me, another silly game on everybody in that I've used a new operator here. I think everyone knows what the value, the string 5 plus 2 would be evaluated by, right? So we have lots of operators that we use all the time. 5 plus 3 is 8. 5 minus 3 is 2. 5 divided by 3 is a floating point number, 1 2/3. But I think fewer people are familiar with modulo. Modulo. So if I have an integer division of 5 divided by 2, I don't get the value 2.5. You remember when you were learning how to do divisions in class, you would work out that 2 divides into 5 twice with a remainder. Everyone remember that? Okay, so we can get at that value with something like the modulo operator. I'm going to show a few examples of this. Do people see what's happening? So 5 modulo 2 lets 2 go into 5 twice with a remainder of 1. So the remainder gets written right here. 2 divides into 6 3 times with a remainder of 0. 7 divided by 2 is 3 with a remainder of 1. So the modulo operator is really useful when you want to do stuff like figure out remainders from integer math. You could do this with something like a modulo 3 as well. 6 is a multiple of 3, therefore its modulo with 3 is 0. 7 modulo 3 is 1. 8 modulo 3 is 2. And again, because 9 is divisible by 3, its modulo is 0. Okay, so if you simply want to ask, is the number provided by the user odd or even, you can use modulo for that very easily. All right. I gave myself quite a complex example on this slide, didn't I? All right, so we're going to ask the users for some number. We're going to try to coerce that into being an integer, and we're going to store it in the variable your number. We're then going to ask, is that number modulo 2 equal to 1? If so, print that it is an odd number. If not, print that it is an even number. Okay, so that's the bit of math that we would want to do. But because users are tricky, it may be that they type purple in response to what number shall I check, and if so, this will produce a value error. Sorry, I should use my terms correctly. It will create a value error exception. That exception can be caught down here. As soon as that exception occurs, it stops trying to execute this code and try. So the minute someone types purple in response to this, it is no longer going to try to execute, to take a modulo 2 from it. We can actually test that on the command line. Let me come out of here. I'm going to move to the directory containing today's code. And now I'm going to run the tinkering script that contains all the stuff from the slides. Oh, not that one, not that one, this one. Okay, so what number shall I check? It's using the division by 0 is not allowed thing, comes from the code on the slide before. So what number shall I check? If I type purple, sorry, I can only work with integers. You see, it didn't type odd or even. It did neither of those. Instead, it tried to process that into an integer. When it realized it had a value error, it triggered the exception and it died. Great. All right, so what specifically is likely to go wrong if you try to open a file? It may be that the file name someone has given you on the command line is not a real file. In that case, you're going to get a file not found, which is a type of IOError. Is it clear why IO appears there? IO in this case stands for input output. So if you are trying to write a file and you run out of disk space, that's an IO error. If you try to read a file and that file doesn't exist, that's an IO error. There are lots of different kinds of things that can happen with this. What if your hard drive is about to die and you try to read a byte from the file and you get a hardware error? That's also an IO error. So IO error can mean lots and lots of things. In this case, we handle it with a generic, we experienced an error opening this file. It is not a recoverable error. Recoverable is one of these terms that shows up in a lot of code, so I'm just using it here. As a result, we don't try to fix it by asking the user to provide another file name. It's a little more economical to just die here. So we, instead of going any further with that, simply execute quit and leave. So that's the kind of exception that the exception handling that we're going to use for now. It's not the most flexible. It's not all that subtle. It doesn't ask what type of IO error it is. It simply says, we can't deal with this problem, we're dying. Okay. Now, I've talked a little bit about lists. I think everyone recalls seeing examples where we've put a whole bunch of numbers in a single set. I wanted to point out that there are other data structures that also exist within Python, some of which are quite useful. So let's imagine that we are trying to create variables that have a kind of a key and value structure. In this case, I'm trying to define a CD from my collection. A little known fact about Professor Tab is that he chose to go to grad school in Seattle, at least in part because he loved the music from the grunge scene. And Seattle, where University of Washington is located, was like the birthing ground of an awful lot of these bands. I mean, if you love Soundgarden or Nirvana or whatever, you have Seattle to thank for that. So, when I went to grad school, I chose a place that had cool music. So I might want to create a dict data structure that represents a particular disk from my music collection. So in this case, I have a CD titled Nevermind. It's probably created before most of you were born. Is that harsh? That's probably true, though. I'm just going to live with that. It's by a band called Nirvana, and it was introduced in the year 1991 when I was a junior in high school, just to date myself a little further. Okay, we see that we have curly braces on this one. The myCD data structure is defined over all of these fields. So myCD doesn't equal just the title or just the artist. It represents all three of these fields. What we have, though, is a key value pair. I might have multiple objects of this structure. The title is a field that I want to capture for my CD. The artist is a field that I want to capture for my CD. And the year is a field. I want to point out that there are a few differences in how these lines are coded, though. You see that these are strings, Nevermind and Nirvana, and the names of the fields are strings. But when you look at the value given for year, there are two things different about it. One is that it doesn't have quotes around it, which means it's being treated as a numeric value, not a string. So I couldn't say June 1991 here. This is not a date field. This is a numeric value. So by entering 1991, I'm having it handle this as a number value. The other thing is that the 1991 doesn't have a comma at the end of it. This is our way of cueing Python to know that there are no more fields to be defined after this. And then to reinforce it, we have this curly brace that ends that block as well. So my CD is actually a complex little structure. And you can address specific information out of a dict data structure by calling on that particular element. So from my CD, I want to retrieve whatever value was stored under year. So I can use the square brackets to index out that little piece of it, and by grabbing out whatever is stored under year, I'm not grabbing back the string year, I'm getting back the number 1991, which is then dumped into this year. So if I were to look at the code for today, all right. So if I were to execute this code, I'm going to grab that little block of it, copy that to the clipboard, start Python, and now I'm going to just paste that in. Okay. So if I enter my CD with caps on the D there, I see that it has stored a relationship between the keys and the values, that title codes to Nevermind, artist codes to Nirvana, year codes to 1991. And I can pull out individual fields by saying, well, just what I did above there, except I stored it in a variable. So I can pull out specific pieces of it by providing the key in order to retrieve the associated value. Okay, so that's a dict, short for dictionary structure. Okay, so let us now see how that plays out in what we're going to do today. I am using another one of those libraries. Remember, we imported sys, we imported random, I think, at some point, or was it math? I forget which library that was. Here we're going to import collections. Collections define some advanced data structures that let you do some really useful things. Specifically, we're going to use a counter object. You can see that it's created right here. Letter frequencies is the counter object, is an example of a counter object drawn from collections. And then we're going to give letter frequencies a string as part of its update method. That update method is going to process this string and store it into letter frequencies. Okay, so when we do that, the letter frequencies is going to remember that it's a counter data structure because it was created up there by that, and it's representing this structure. Now, how's that similar to a dict? We saw the dict just the slide before, right? So here we have a key for A, a key for B, a key for R, a key for C, a key for D, and we have counts, numerics corresponding to each of those. Okay, so let's see if we can work through this code interactively. I think that will help make this even clearer. I'm going to just run that first part. Okay. All right. So if we see letter freaks has 5 A's, 2 B's, 2 R's, 1 C, and 1 D. Okay, I'm going to ask a couple questions about this. Why are the letters in this order rather than in alphabetical order?
As it picks up the letters in the word.
Right. Because the letter freaks is not going to automatically contain every letter. It's instead going to contain it's going to instantiate a new key every time it encounters a letter it's never seen before. So A, B, R, all three times it encounters those first three letters, it has to create a new key corresponding to a letter. And yet, when it hits this fourth letter, when it hits its second A, it recognizes that this A is just like the A I saw before. So instead of creating a new key to represent that this is the fourth potential key I've observed, it can instead increase the counter for A's. Abracadabra just happens to be overloaded with A's. Look at that, 5 of them. Now I want to note that this is not the only way we could have instantiated that. You see that we created letter frequencies by this call to counter. This is a constructor that allows us to make this function, but we could also do something sneaky like write abracadabra here. Is the result the same? It is. So the constructor can just create an object with nothing in it for you to populate later, or at the time you construct the letter frequencies, you can give it the string you want to build it from. Okay, so what about the Poconos? O before P, before C, before N, before S, and 3 O's, and then 1 P, 1 C, 1 N, 1 S. So counters are, and I want to ask one more thing. Folks recognize why this is a dict as well, correct? It's still a dict because it is one data structure that holds a key matched with a value that is a count of how many times that's happened. Okay, great. So we're going to use, I'm going to do one other thing. So let me return to our abracadabra letter freaks. Okay, so here we have the original letter frequencies that we had. I want to point out that letter frequencies is not limited to holding the result of just one string. I'm going to add another string to it by using the update function. Anyone have a good suggestion for a word here? Let me see. Let me see. How about the word baby? I'm going to add the word baby. Okay, so having added baby, I'm adding the letter composition of the word baby on top of the letter composition of abracadabra. And that, in some ways, that added to the information that was already there. The A and the B keys already existed. We just increased the counts. But Y was a letter it had never seen before. So even though it had already started filling this out, seeing the word baby gave it a letter it hadn't experienced before. Yes?
For the Poconos, I noticed you didn't count P as first, it was O. Why does
That is really interesting.
And for the Abracadabra,
I really don't know why. When we looked at Poconos, yes, I would have thought that it would have created the letter P first. So what happens if, let's create an empty one. Oop. Update Poconos. That is odd, isn't it? Huh. Well, I don't have a good answer for you. I would say, though, that in general, a dict structure tends to be somewhat loose about the ordering of the keys within the structure. It doesn't matter what the ordering of them is here, because the way that you would access that would look like that.
But could it be, the reason could it be because O has more frequency, it appears more than the other letters, maybe?
I don't really know.
Was also A in that case,
Yeah.
was like, it appeared more than the other.
All right, I will try one of the most entertaining states to try to spell. Mississippi. All right, so let's see what happens. S is number 1, so it may be that it's working with the higher frequencies, yeah. Interesting. Okay, so though you probably shouldn't count on the ordering of keys in these cases. But it's a good observation. I didn't notice that when that one went by. Okay. So counters are really helpful as a way of doing these counts on the fly. And we're going to use that in the code today. All right. So I'm now going to pop out of this and move over to our code. So all of the examples that we did in the slides appear here in the tinkering code for today. All right. But let's move to the source code for goal 4. Today is the 4th day of class, so we're going to add some new items. So we see that we have import sys. That's because we're using information people have fed us on the command line. We're going to import collections because that's where we can get a counter object. We've updated our version number to version 0.4 because it's day 4. We still have our code here for grabbing out the FASTA file name. All of this stuff was code that we had on last week's session. Now, though, when we open the FASTA file handle to create the FASTA file object, we've put it inside a try because that action, the action of opening the file, can create an exception. And we specify that the exceptions we're interested in looking for are IO errors, input-output errors. If we encounter one of those, we are not going to try anything heroic like asking the user for another file and then repeating to that code. Instead, we're going to just die, right? So the software could try to fix the problem or look for common ways that people might misspell stuff, like try for the FAA in addition to the FASTA extension or something like that. Instead, we're simply going to die. So the software says we experienced an error opening the file and we quit. That's all pretty straightforward. Last week, we had set up our code to begin counting how many different proteins there were in the database. But we're also going to add a counter here called letter counts. Now, we have this little challenge that we want to do one kind of action when we encounter a FASTA line that starts with a greater than symbol. Remember that the FASTA sequence database has its accessions starting with greater than symbols. So effectively, as we pass through these files line by line, a line is either starting with a greater than symbol, in which case we must handle it like a new protein, or it's starting with just a letter, which tells us that it's sequence instead. So as we go line by line within the FASTA file, we need to ask, does it or does it not start with a greater than symbol? In this case, we asked what the first element of this line is, which is not this line square brackets 1, it's this line square brackets 0. Remember that computer scientists, the first number is 0. All right, so we check to see if that first character is a greater than symbol. If so, what clever things do we do when we encounter a new protein in our software? We do just one thing. We don't read the description. We don't even ask, have we seen this accession number before? We simply add 1 to our counter, right? So we're not doing a very subtle evaluation of how these things are formatted, etc. We're just going to add 1 to accession count. But since we created this if to check if the first character is greater than, we gave ourselves the ability last week to detect that we needed to add 1 to our accession count. But this week we're adding an else to it. Because remember, there's this other possibility that this is a line of sequence. If it's a line of sequence, we want to add it to letter counts. So if you have 10,000 or 20,000 lines within this FASTA file, for every one that is not an accession line, we're going to add to our frequency counts for how many times each amino acid appears in the sequence letters. Letter counts update this line. Remember that it's always a good idea to close the file at the end. And then we need to be able to report back to our users what did we accomplish with that time. So we're going to report how many different accessions there were. This code was there last week. And this time around, we're going to give them a badly formatted line that says, this is how many times each amino acid appeared. That's the letter counts down there. Okay, so does it work? First off, I need to get out of Python in order to be able to run this properly on the command line. As I do my quick directory of the files called .py, I see goal4. That's the one I'm going to run. So I simply say Python goal4, and then I must give it on the command line the name of the FASTA file we're going to process. Having entered all that, I hit enter, and look at that. It was pretty fast, wasn't it? So being able to read a FASTA file of 4,000 entries took less than a second, and we see that this is how many times each letter was observed within that sequence database. So we have 26 letters. Do we have 26 entries in the counter object? Anyone see any letters that are unusual? Okay, what's a letter from the alphabet missing from that collection? Anyone see a B? Okay. It is possible, although confusing, that if you're reading a biological database, especially one that's manually curated, that you would encounter letters that should not be there. If, for example, you were working with databases that are formatted in a particular way, you might see that the last letter of each sequence was entered as an asterisk. Some FASTA files you see in the wild will use the asterisk to represent a stop codon. So every sequence will terminate in that. However, and if you're working with a manually curated sequence database, you may see that someone's made an error. Maybe they've given you a B character or an X character or a J character. Sometimes those are not errors. Sometimes you might see the letter U used for selenocysteine, for example, or you might see O used for ornithine. Those are not common amino acids, but some sequence databases out there do use them. So ideally, we would have 20 different letters here. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I'm sorry, this actually rolls over. Haha. Oh, look at that. We did have a letter hiding in there. We have a \n. All right, so that is a little confusing, isn't it? Why would we have a \n in here? Does anyone know what that represents? Unidentified. Ah, okay. It's actually less subtle than that. In this case, \n is something that would be immediately recognizable for a computer scientist, but maybe not so much for somebody who actually looks at data more practically. When we read a line of text from this FASTA file, we are considering every character in every line. And these lines stretch from a first letter of sequence at position 0 up to the end of the string. But at the end of the string, the software is noticing that the lines of text all say, go to the start of the next line. It's called a return carriage. And back in the days that we used line printers, those were, that was a literal direction to tell the print head to move back to the start and then rotate up a page. So this is called a carriage return line feed. So in the old days of ASCII, they actually created a character that means go to the start of the next line. This \n is what that is. Okay, so \n is a special character. It's not a printable character in that sense. But because we didn't tell counters, the counter object that we created, that we're only interested in letters, it included it anyway. Okay, so we might have seen a star. We certainly might have seen these \n characters. In this case, it caused us this oddity. But that's all we're going to do for today. Next week, we're going to start talking about visualizing these data so that you can get bar graphs. Because frankly, I find this a little hard to read. I mean, if I'm just looking at this counter report here, is it immediately obvious which amino acid is most frequent in that set? It's a little difficult. They're all large numbers. And a good visualization makes all the difference in the world. So next week, we're going to focus on making some bar plots that enable us to dissect this information a lot more rapidly. But for this week, that's Python for Biologists, and thank you very much for coming. I appreciate it.